Alright, we're going to talk about ideal op-amp circuit problems. Now, op-amp circuit problems are not difficult if you can remember 3 rules of an ideal op-amp. Then you can treat it pretty much like regular nodal analysis. The first rule is that no current enters the plus or the minus pins. The plus or minus pins of the op-amp, which are right here, wires entering the op-amp, they can hold, this node can have a voltage, but no current can flow into the op-amp on either side. So this means that the current coming in right here is going to be equal to the current going down this way. It also means that there's no current in this branch here. This power supply might be supplying, say, 5 volts, but none of that, it doesn't produce any current since no current can go into an op-amp. The second rule is that the plus and the minus pins have the same voltage. This means that this 5 volts, this example 5 volts right here, is going to be 5 volts on here as well. You can treat both the plus and the minus pins as one node essentially, as far as voltage is concerned, not current. The third rule of ideal op-amps is the op-amp can source or sink any amount of current on its output. So here, on the output voltage, we don't know if the op-amp is sinking current or sourcing current. This allows it to control the whole circuit. Now, when you have op-amps, you have 2 special cases, not special cases, but common cases of op-amp circuit configurations. One is called the inverting op-amp, which looks like this, and the other is the non-inverting op-amp, which looks like this. These configurations you'll see a lot. So if you see this configuration in a circuit, you can automatically plug in its formula, which I'm going to derive right now, which is going to be the relationship between V in and V out. We start by recognizing that this node right here is going to be 0 volts, since the positive pin is connected to ground, and since both pins have the same voltage, the negative pin is going to have 0 volts as well. We can specify currents I1 and I2, which are the currents going through these resistors. And since we know that Vin, we're assuming Vin is a positive voltage, so we know the current flows from high voltage to low voltage, so I1 points this way. And I2 points this way because since no current divides here, it has to be in the same direction as I1. And since they're all essentially the same branch, since no current divides, we can say I1 equals I2. And then doing nodal analysis, we can say I1 is equal to Vin minus 0 over R1, which is equal to I2, which is 0 minus V out over R2. And solving for V out, we can say V out equals negative R2 over R1 times Vn. And this is the formula for an inverting op-amp circuit. This is important because we know that whatever voltage we put in, the voltage sign will be flipped since we have the negative sign, and we know that since it's R2 over R1, we can make it the output voltage larger or smaller than our input voltage. Now we'll go to the non-inverting op-amp case. We'll do the exact same thing. Since we know that the voltage V in at this positive pin is equal to the voltage at the negative pin, we can just say that V in is the voltage right here on this node. We know that this is ground, so we can say that the current I1 is flowing this way from high to low. And since current doesn't divide into the op-amp, I2 flows in the same direction. And for the same reason, we know that I1 equals I2. I1 is equal to Vn minus 0 over R1, and I2 is V out minus Vn over R2. Now we're going to multiply by R2. We have Vn times R2 over R1 equals V out minus Vn. We can say that V out equals Vn times R2 over R1 plus 1. This is important because we can see that whatever our V in is, it cannot be less than our V out, because R2 over R1 plus 1 cannot be less than 1. It has to be greater than 1. And unlike the inverting case, the input voltage maintains its sign for the output. So if it's positive input voltage, it'll be positive. If it's negative, it'll stay negative. So those are the two cases, inverting and non-inverting op-amp circuits.